I believe we have now an attendance already. So we're moving ahead in this afternoon here in Porto, again for a new webinar on the areas of power and energy, but also associated areas. Today we have an interesting title, an interesting theme to discuss here from 2 points of view, related with operations research and AI for electric mobility services. We'll be having here today and this afternoon Carlos Silva and Leonardo Bittencourt to present these different views. So we have this perspective on the data-driven services that EV charging services can unlock altogether. So what can be exploited from the grid perspective in terms of users and as adopters of EVs, and how to cluster them and how to manage all of them for specific benefits. But then we have the view from Leonardo, which is also joining from a complementary view on the side of logistics. So how to adopt business models, how to make use of electric mobility overall and sharing and individual mobility and so forth. Basically to allow this combination between what we hope to be a joint endeavor on the combined service for the end user. So join us here today for what I am expecting. I'm convinced it will be a very good discussion from 2 angles. So we'll start with Carlos, then we'll have Leonardo right after, so it's a 20-minute each presentation. We'll have room for questions and for curiosities, so feel free to use our Q&A board to introduce your questions. We'll make sure to post them to the speakers, and then with the discussion to create a bit more dynamics into this interesting field. So welcome everyone to this session, and without further ado, I'm introducing Carlos and passing on the floor to Carlos to set the view and set the scene on the driven side of EV charging. So go ahead, Carlos. We'll see you in a bit.
Hi everyone, thank you for your presence in this webinar. My name is Carlos Silva, and my presentation is named Data-Driven Services in EV Charging Stations. So first of all, I would like also to thank my team, which is right here on the bottom corner. So starting by the introduction, we have 2 main reasons behind the topic of this work. The first one is that we do have a wider adoption of electric vehicles. You can see here on the right the millions of sales per year until 2030, and it rises exponentially. This causes in turn some challenges in terms of grid operation. We can have an increased demand, so in terms of peaks, and also a change in the demand patterns, which can cause congestion problems and add an overall stress into the network. And second, we must think of electric vehicles not only as a mobility asset, but as a distributed energy resource. For example, we can think about load shifting and also recent capabilities of vehicle to grid that allow new services to be offered to the electrical grid. Second reason is that if we have a wider adoption of electric vehicles, then we need an adequate charging infrastructure. So more charging stations that are available, and that those charging stations have to have a service that is profitable. So the 2 main questions that we propose for this work is how can we control the EV charging process to improve the performance of charging stations? And the second one is, can the charging process be simultaneously optimized for the charging station operators and EV owners? So to try to answer to the first question, in terms of EV charging control, we have 2 main approaches. The first one is direct control, which is connected to, for example, smart charging concept. We have data that flows between the utilities, the charging station operators, and the electric vehicles. And then we try to optimize the charging process, normally by controlling the actual power consumption time series according to the external factors. And the second approach is an indirect control, in which we try to design incentive mechanisms that we believe that can influence at some extent the behavior of users. And in this work, we are going to try an indirect approach. So one example of an indirect control approach is dynamic pricing. Dynamic pricing is what you can see here in the figure on the right. So you have a price that varies throughout a certain time horizon. And this price varies because we have different operating conditions, and so the price can adapt to those changes. This is a mechanism that relies on the EV owners having flexibility. So we believe that at some extent we can control or influence the behavior of the consumers. And this is also very closely related to the concept of elasticity, because we know that if we give a certain price signal, so that if there's a percentage of variation in price, we also expect a certain percentage of variation in terms of demand. And finally, just to note that this is not specific to electric vehicles. This is also a concept that is applied in other sectors, such as the residential, to enable, for example, demand response programs to be implemented. So why dynamic tariffs? Because then we can adapt the tariffs to specific operating conditions, for example, electricity prices in the market, renewable energy generation, predicted occupancy, among others. And also because we can direct the service for the goals that we want, such as reducing operational costs, the carbon emissions, increasing the user satisfaction. So the question that remains is, how can we generate the dynamic tariff incentives? At first, I'm just going to give you an overview of what we are considering as an EV charging station. So a charging station is where we have a charging service. We assume that a fleet of electric vehicles arrive, they have a need for charging, they have plugs, the plugs are connected to charging points, and the set of charging points compose a charging station. And here consumers can start and end transactions, and also usually there's some kind of platform that allows the interaction between the consumers and the charging station for them to start and stop transactions, to check historical transactions, etc. And a key concept or a key component of the charging station is a charging station management system, which basically enables, monitors, and manages the charging processes and the transactions, which in turn means that it's also responsible for the flow of data that is generated with the charging process. But we consider that EV charging stations are not isolated, so they are consumers, they establish contracts with electricity retailers, and these retailers in turn participate in electricity markets, for example, the Iberian day-ahead market. And also they can have renewable energy generation on site, which can have or not surplus, which is also very interesting for this problem. And what we want to do is leverage on this type of infrastructure to create a service that is data-driven. We're going to see that in the next slides. For example, a dynamic tariff service with the main goals of trying to improve our knowledge on the consumer's elasticity, improving the performance of charging stations by integrating the data that is available within the charging process and other sources of data also, but without knowing a priori the knowledge, without knowing the elasticity of the consumers. So we are going to do this by trying to combine the data that flows in the infrastructure I just showed you with AI and operations research. Just a note on the project. So for now we are talking about concepts, but this is within the scope of Interconnect project. Interconnect is an European project, and this is a task that relates to EV charging stations, specifically in supermarkets. And we have a commercial pilot that is going to be operationalized, so a dynamic tariff mechanism in a retail chain in Portugal, at least in one store. And our main goal is to improve the performance, for example, in terms of increasing the profits of the charging station. And this project has some very particular characteristics. We have slow and fast chargers. The slow chargers can have 4 different charging tariffs. And the main characteristic is that it's not a pure dynamic tariff in this project, because we are considering that we only have charging tariff discounts. And finally, there's this idea of euros per minute, which is going to be important because we are charging a service of parking or charging in the station, and not selling the actual energy that is consumed. So trying to categorize the mechanism we are creating. In terms of pricing type, so how the prices are structured from the point of view of the users, it is a non-personalized incentive, so it's the same for all EV owners. It's not for individual EVs, and it's profile-based incentive. So we have a price that varies in different time intervals versus a session base in which the price will be for a complete charging session. In terms of pricing implementation, so what was the approach to set the actual prices? We did this in an offline way, in a day-ahead operation. So today we are setting the incentives for tomorrow, and we are computing these incentives for a specific charging station. A charging station can belong to a network of charging stations, but we assume that they can have different operating conditions, so they deserve different incentives. And finally, in terms of address flexibility, we can think of asking users, can you increase the duration of your charging? Can you decrease the amount of energy that you consume in this charging session? Can you change the location of your charging station? Can you charge in another charging station? But this is not the kind of flexibility that we are addressing here. What we are assuming is that the EV owners can arrive later or earlier in time, so to proceed with the charging service. In terms of data that falls in the charging stations, when there's a need for charging, the AV goes to a charging station, it starts a transaction, and between the time that you start and end your transaction, you're obviously charging your EV battery, but there's also a flow of data that is generated. Specifically in this project, we identified two types of data. The first one is the transaction metadata, so global information on the transaction, such as what was the station, the charger, the user, the total duration, energy, cost, but also the metering data, so the actual power consumption time series for a specific transaction. And this data allows us to create new data. For example, occupancy. We can think of occupancy at store level, so how many electric vehicles are parked or charging at any given time. And also, this is important because, as I told you earlier, for this project, we are talking about selling the service and not selling the energy that was consumed. Another important data that you can generate is idle time. So trying to know the amount of time that EVs are still parked, but they are already not charging. There's some kind of flexibility there also, but we are not using that right now. So now entering the actual service that we developed, we have what we call a dynamic tariff mechanism. What this does is it periodically requests the data that I just showed you from the charging station management system. It also gathers data from external sources, for example, electricity prices, weather data from a weather provider, and it feeds all of this information to a forecasting service, which gives us a day-ahead prediction on occupancy and also renewable energy generation. Then we feed all of this information into an optimization service, which computes the actual incentives that are going to be communicated to the users. We assume that there's some kind of integration platform for which enables the interaction with users. It periodically requests from our service the incentives and then broadcasts them to users. So now, going into a little more detail on the forecasting service, specifically the occupancy forecasting service. So what we did is that we tried to follow a conventional approach to define a machine learning model. We started with the data engineering pipeline. We started with two base variables, so the occupancy and the numerical weather predictions, and we created new variables that we think we can extract more information from those variables. For example, calendar variables, endogenous variables from the occupancy, and the exogenous variables from the numerical weather predictions. Then we tested different combinations of these variables over multiple classification and regression models. We went from naive approaches to machine learning and deep learning based models. And finally, the output. The output is a discrete variable. which represents the occupancy level in the charging station and goes from 0 to the maximum number of plugs that are available at any given time. Now into more detail, we did feature selection, model selection, we tuned the hyperparameters, all of these with concerns for cross-validation. And then what we did is we defined a model that is specific for a certain charging station, but also, and because of the particularities of this project, specific models for slow chargers and for fast chargers. And what you can see here in the figure on the right, it's 6 days of trying to predict in a day-ahead manner the occupancy for slow chargers. And finally, for the forecast, we have different metrics that we selected for evaluating the model, the F1 score, the precision, the recall. And what we did is we built a naive model first. So in this case, a model that assumed that the occupancy for tomorrow is equal to the occupancy of yesterday. And in case of being the weekend, it's equal to the prior weekend. And then we benchmarked all the models that we had available against that naive model to perceive the relative improvement that we could achieve. And what we have here are the preliminary results that show that relative improvement. Now, going on to the optimization service, we think of the optimization service as something that models two agents that have conflicting objectives. The charging station aims to maximize the profits, while the EV owners aim to minimize their charging costs. We know the charging station has some predictions on occupancy, renewable energy generation, and also that it is informed of day-ahead electricity prices. And for EV owners, we know that they can shift their charging in time, and we know what we assume is that they can have an optimal reaction to the incentives that they receive. But the main complexity of this optimization comes from the fact that the charging stations want to set incentives, but they don't know the reaction. So the elasticity, as I told you before, is not known. And for EV owners, they want to react, but they depend on the incentives that are provided. So there's this problem that resembles what in the literature is assumed as a bi-level optimization problem, and is very used in situations like this. I'm not going into many details on the formulation, but you can see here some examples of constraints we are considering. For the charging station, we can assume that if incentives are generated, they must improve the profit of the station. For this specific project, we are dealing with discounts, so we can also think about blocks of discounts. So constraints on limiting the number of hours in a day that you have incentives, the number of consecutive hours with the same incentive. This is also important to have a more efficient communications with EV owners. And from the perspective of EV owners, we have to account for the physical limits of the infrastructure, so the maximum number of slow and fast chargers, the plugs that are available, and also in terms of flexibility. So we also limit the slow and fast chargers by a flexibility indicator, in which for a first estimate, we assume that we can extract it from historical data of occupancy. And finally, can also assume that the daily charging costs must be reduced due to using the incentives generated. And these are just some examples on the results for the optimization. So going from the top to the bottom, we have the electricity prices. Then we have the occupancy predicted and the flexibility limits. In third, we have the occupancy shift. And finally, the discount that was generated. And the first thing we can see is that we are generating incentives for hours with low electricity prices, and that is very important for us to increase the profits. And the second thing we can see is that we have here an hour on the left that has a lower electricity price, but there was no incentive allocated for that hour. And this is just to bring you the importance of having these flexibility limits well estimated, because in this case, it was easier to allocate the incentive for the other hour, which had a higher electricity price slightly. And this is just another example. In this case, we have more hours with lower electricity prices. So the optimization was able to set up an entire block of discounts of 3 hours that you can see here. And you also can see in the third plot the occupancy shift that we expect from those incentives. And finally, how can we integrate this type of services in EV charging stations? So as I told you before, we assume that there is some kind of integration platform to communicate with users. Well, in our case, in our project, in fact, there is. We are using a mobile application and every day we are sending a push notifications to users, which establish the incentives for the next day. So users they can consult the application and they can choose when to charge by looking at the incentives. And when we look at in the longer term, what we are doing is accumulating data on the reaction that users have to these incentives. So what we are accumulating is the actual elasticity data that we wanted and did not have. This means that we can then further improve the modeling because now we have elasticity data. We can think of new approaches and also compute incentives that are even more efficient. We can also think about new products. For example, the concept of elasticity matrix is very important. We can ask ourselves what will be the effect of a certain price signal on, if the price signal was sent on T1, what will be the effect on T5? And also we can think on new approaches. Should we do personalized incentives instead of the same incentive for all EV owners? Should we cluster consumers by the levels of flexibility they provide or their reactions to the incentives? Just some ideas. And finally, the generic impact we expect on the EV charging station. So we have a varying electricity price. We have incentive blocks generated and allocated in these hours. And then what we expect is to see a shift in occupancy in some hours, and consequently a shift in the electrical load of the charging station. So this allows us to reduce costs, increase self-consumption, or fulfill any other objectives that we propose. Just some conclusions for this presentation. So I showed you how a dynamic pricing can unlock the potential or even increase the flexibility of electric vehicles. The dynamic pricing is the ability that we have to vary the price according to operating conditions for the charging station. And this in turn can facilitate, for example, the integration of renewable energy resources. In terms of the state of art, we found that there are different approaches found for this type of problems. One of them most found is this concept of bi-level optimization. So thinking of the charging station and the EV owners as having conflicting objectives. And also some research gaps are reported. The main one is a critical lack of elasticity data, especially for the EV sector, and also lack of user studies and lack of services that are in fact operational. And with our current project or our current methodology, we are extracting the data from these stations, combining it with AI and operations research techniques, and we join these forces to create incentive mechanisms. And this can be used as a starting point. So we can let the service operational, generate elasticity data, and then further optimize the modeling and the incentives that we provide to our users. Thank you.
Thank you very much for the presentation. Going to the questions, so just checking the audience if we have any questions to pose you. If they don't, I can start with one until people are a bit, let's say, unlocked to pose some questions. You were saying about the incentives to the end users, and you discussed briefly the discrimination to these incentives. Is this discrimination in mind? Have any sort of more concrete approach to it? I'm remembering this part of flexibility. One of the things that's to be considered is the participation and the certainty of having an electric vehicle to be flexible about the charging. The electric vehicle may not be there. So in this kind of incentives, would it be possible, or how would it be possible to have a sort of an historical participation to actually influence the incentives? Roughly to say that if you are a well-behaved participant, you should have advantage on having a good participation historic basis. So any thoughts on that?
Yeah, so that will be one of the next steps that we have in mind, because we are operationalizing the service. We are going to generate data, and from that data, we are going to try to extract if, in fact, users are reacting, and if users that have different levels of flexibility are reacting. And that brings me to one of the questions that I was addressing. Should we, for example, try personalized incentives? Because if we discover that different users, some react, some do not react, maybe we should make incentives just for the ones that react. Should we make different levels of incentives for the ones that react in a more optimal way from the perspective of the charging station? So I think there could be different approaches in terms of accommodating the results of the participation in the actual service. Yes, so that's a next step when we have the data.
Okay, very good. Regarding the testing now that will be done, can you talk a bit more of the validation? Because you were building these models based on existing data, but soon enough there will be an opportunity to start taking this into the field. So can you just talk a bit more of what to expect? What will be the next approaches towards, even regarding the part of modeling? How would that influence the models that you have used in terms of the predictive side to the behavior of the participants, of the EV owners?
So yeah, in terms of the data that is going to be generated, in terms of forecasting, obviously this is a challenge, but the forecasting model should adapt to the different behavior that will occur in the future. But this is more interesting in terms of optimization. We can think of different approaches to integrate the future data that will be used. So first we try to build this with the historical data. This is without prior knowledge on the actual flexibility or elasticity that we have available. And then when we have the actual reactions, we can try to implement some, for example, constraints on the optimization problem that are focused on integrating the elasticity. We can build the elasticity matrix that will be other approaches to compute more efficient incentives, because we are talking about reactions that already happened. But these are some of the ideas that we have. So new data is going to come, and we are going to integrate it either on the optimization problem itself, or we can think of outside of optimization and rely on elasticity matrix, for example.
Since we're talking about optimization too, we have a question here from Pedro Leão, which relates a bit to what you were just explaining. And the question goes along regarding the models, which kind of models work better to resolve optimization problems? So you can perhaps refer to what was the results that you achieved with the different models that you tried.
Yeah, we right now we are working only with one. We assumed what we found in the literature is that the bi-level optimization makes sense in terms of formulation, because there's this dependency that I talked about. So we don't know the incentives, but we don't know the reaction. So we have to set incentives without knowing the reaction, and this allows us to do two things. First, to assume an optimal reaction, and this is obviously a first estimate, and that's why that future data is going to be important, because this is not true. That there's not going to be an optimal reaction, but it allows us, this type of formulation, to have a starting point in which both agents have optimal results.
Okay, so yes, just to answer a quick question, we are going to share the presentation live. And another question, okay, from Brida, we have here for dynamic tariffs, how will the users get information in advance about electricity prices? We need to subscribe in advance for using charging stations. This might be challenging for users. Considering that this is shopping while setting, users spend a few hours on flexibility is still possible to get. So I guess there's a big question there. So let's try and simplify this. So how do you think, how easy it would be to share within the users this flexibility provisioning in the way that they could perceive being regular users of spaces such as supermarkets, for instance? What do you think should be the approach here? Because as you said very well, Carlos, there's a dual role here from the EV owners and then the charging station owners.
So EV owners they don't need to have a lot of information. They don't need to know the electricity prices, as I think the question was asking. The charging station knows the electricity prices, and the optimization problem tries to direct the incentives to hours with lower electricity prices. So that's not a concern of the EV owner. In terms of communication, what we are doing, I think it makes sense. So we have a platform that integrates that is responsible for the interaction between the EV owners and the charging station, and we took advantage of the existing infrastructure of this platform to add a new feature in which incentives are able to be consulted. So every day you receive a push notification, and you can consult what are the available incentives for tomorrow. So if something like between 2 and 4, you have a discount, or you have some kind of incentive. I think that's an efficient way, but that's a good question, because it's difficult. We don't know if the EV owners are actually going to appear that hour or not. You estimate that from the data. But in terms of communication, I think it's the simplest way is using existing platforms, so things that do not need new infrastructure and new platforms to integrate.
Okay, then for a very closing question, so a brief answer, please, so we can have also Leonardo in. There's Andres Cortez that's asking if you consider robust optimization, especially in the case of the analysis of extreme scenarios.
No. At this time, no.
Okay, that's as brief as the answer could be, so thank you very much. So I believe that we can now pass on to Leonardo. So Leonardo will present also a related theme, so more on the opportunities for electric mobility. And again, using optimization as grounds, considering the part of shared business and shared infrastructure and assets, in this case, electric vehicles and the car sharing too. So Leonardo, the floor is yours. So if you could just share also the presentation from your side, we'll be glad to hear also from you, and later on for the Q&A session. So go ahead.
Thank you for your presentation. Hello, everyone. My name is Leonardo, and today, are you guys hear me well? Can you see my screen?
Yes, we can. All fine, and the sound is better.
Thank you. Okay. So today I'm going to present my latest work entitled "Assessing the Challenges and Opportunities of Electric Mobility through the Optimization of the Car Sharing Considering Demand Uncertainty." So starting with a brief summary, I will present an introduction of this work, followed by the motivation, and then I'll present the methodology and a case study, and then I'll present the results and the conclusion of this work. So electric vehicle sales is increasing in the world, as we can see here in this figure, but the EV market is still low, even with this increase. So we need to start and think in some new business model in order to increase the EV penetration. And the share economy is also another growing phenomenon. And in the mobility context is also known as a car sharing. And when a car sharing company is made full of electric vehicles, we normally call that an e-car sharing business model. They have different systems. They are unique systems, and they are the one-way, the route trip, and the free floating. In the one-way, people can rent a car, an EV, and they can return it to another different station that they rented before. In the route trip system, they must return the vehicle in the same station that they rented the previously. And finally, in the free floating, there are no stations. There is only one concession area of the company, and they can rent and return it anywhere. But despite being a growing, the car sharing growing, there are uncertainties that affect the revenue of the company. And the uncertainties are related to the rental demand. But in the other hand, we have the distribution system operator that they expect to reinforce the grid for a normal load increase. But with the increase of EV penetration and therefore the EV charging, it is expected that the reinforcement costs increase even more. So there are two solutions here that could help the DSO. The first one is the coordinated charging of the electric vehicles, which is also known as a smart charging, but they only shift the charging from peak times to off-peak times, and this could be achieved using dynamic tariffs. And the second option is the vehicle to grid, it's also known as V2G, and they not only shift the EV charging from peak times to off-peak times, but they also discharge the EV into the grid so they can shave the load peak. So these two options could help the DSO. So this leads us to the motivation of this work, because e-car sharing can play a key role as a new business model, but they still face some problems. These problems are related to the uncertainties. And this leads us to the two questions that we are trying to answer in this work. The first one is how uncertainties affect the e-car share revenue. And the second one is can the e-car share incorporate with the DSO? So following to the methodology of this work, we developed a two-stage stochastic model in GAN's MATLAB. And for this, we have created different scenarios to assess the decisions of both agents, the e-car sharing and the DSO. The e-car sharing model is based in the one-way system, which people can rent a car in a station and return it into a different one. The energy tariff is based on the distributional local marginal price. The distributional local marginal price is an energy tariff that is based on the power consumption of the node of the bus. So if I have a high power consumption, a high power, the energy tariff will be high, and if the power is low, the energy tariff will be low. For our cases, we are considering the decisions with and without V2G, and we are considering the uncertainty in the rental demand. For our DSO model, we are considering the EC optimal power flow using the branch flow model. The branch flow model is a model that is based on the second order point programming, which in this work is linearized by the global polyhedral approximation. Here we can see that the flow chart of this proposed methodology. There are some inputs related to the power grid and some inputs related to the e-car sharing. The power grid, with these inputs, we calculate the DLMP without any electric vehicle, which will be used as an input for the two-stage stochastic model. For the e-car sharing parameters, we have prices, costs, and constraints, and we also have our scenario generation based on the random variables that are related to rental demand. So with this, we have our joint model of the DSO and the e-car sharing in the two-stage stochastic model. And as the result of this optimization, we have our outputs related to the e-car sharing planning and the DSO planning. In the e-car sharing planning, we are considering for our first stage decisions related to the siting and sizing of the charging stations and the size of the EV fleet. As a second stage decisions, we have the operation of the e-car sharing that are related to the accepted rentals, the charging planning, and the relocation planning. For the DSO, our first stage decisions are related to the reinforcement of the cables. So some cables will need to be reinforced. And for the second stage decisions, we have the operation of the power grid. So for the case study, we developed 4 case studies, and the objective of these cases are to investigate the decisions with and without the power grid constraints, and with and without vehicle to grid. So here in this table, we can see that the base case, we only have the power grid constraints, and we do not have any kind of electric vehicle. For cases 1A and 1B, we have the optimization without V2G and with V2G respectively. And similar for the cases 1A and 1B, cases 2A and 2B have the power grid constraints. In the planning horizon, we are considering 1 year for the planning horizon, and for the operation planning horizon, it's 24 hours with 1 hour time interval. For the power grids parameters, we are considering the IEEE 33 bus test system, which is this one here, and the same demand load shape for all the loads here. The energy price at slack bus, which is the bus 1, is $20 per megawatt hour, and the voltage limits are within 0.95 and 1.05. We are also considering a pool of cables with different capacities, so it can give flexibility for the DSO's decision. For the ECA sharing parameters, we created a scenario generated algorithm based on the real data, and this real data contains more than 600,000 of rental trips collected over 5 months. With those rental trips, we created a kernel distribution of the start trip probability density function, which is this figure 1 here. For the origin destination and the trip duration, we used a uniform random distribution. And here are the positions of the grid. And we are disregarding position 1 because it's the substation, and we do not want to allocate any kind of load there. And for the trip duration, we are considering only trips that take 1 hour and 2 hours because the time interval of model is in hour. It's important to notice that for real cases, it's necessary in-depth study, especially to assess this origin, destination, and trip duration. Following for the scenarios, here we are considering only 2 scenarios because you want to evaluate the decisions in low rental demand and in high rental demand. Here, the low rental demand, named scenario 1, have 20 total trips with 20% probability of occurrence. The right rental demand, named scenario 2, we have 40 total trips with 80% probability. Here is an example in how those scenarios look like. And here, for example, is a 1 demand, and someone wants to go from position 29 to position 13. The trip will start at 6 o'clock and will take 1 hour. So it will arrive at 7 a.m. at position 13. So for the scenario 1, we have a table like this with 20 lines, so 20 demands. And for scenario 2, we have a different table with 40 lines, which are 40 demands. Finally, we have these additional parameters for the ECA sharing. There are prices, costs, and technical parameters of the charging stations. Following to the results, here we have a decision summary of the cases. Just to remember, here in case 1A, we have optimization without V2G and without power grid constraints. Here we have optimization with V2G and without power grid constraints. Here we have optimization without V2G again, and with power grid constraints, and here with V2G and with power grid constraints. So at first, we can see that the total profit in descending order, the highest profit is the case 1B, followed by the case 2B, then the case 1A, and then the case 2A. We can expect that case 1B presents the highest profit because here we have the flexibility of the V2G, and we do not have the power grid constraints. On the other hand, we can also expect that in case 2A have the lowest profit here, because here we do not have the flexibility of V2G, and we also have the power grid constraints that limitates my power flows. So we can expect this, these two ones are in the borders. We can also see that the first stage decisions here are the same for all the cases, and the rental and relocation is also the same for all the cases. Here, the rental relocation, the rental and the relocation. So this leads us that our methodology is not affecting the customer services. And we can also confirm that because our meeting demand is the same for all the cases. So it only is affecting the charging costs. So you can see here that my charging cost is different for each case. And finally, we can see that the simulation time considerably increased in the cases when we have the power grid constraint. Here it took only 7 seconds, 4 seconds, and here it took minutes to solve the problem. Following the results, we have here the charging power in the cases 1A and 1B. And just to remember here, we do not have the power grid constraints, and here we do not have V2G, and here we have V2G. And first, we can see that there are more charging events in the scenario 2 here, and this is because of their high rental demand. So people rent the EVs, and the EVs must, they discharge because of rental, and they must charge in order to meet more future demand. So because of that, we have more charging events here in the blue curve. But in the red curve, you can see that there are mostly no charge, and this is because there are no rental demand, and the EVs do not have flexibility. So they most of the time they stay idle into the stations. Here in the second case, when we have V2G, we can see that there are more power injection here, followed by high consumption scenarios in the scenario 1. So this is because of the low rental demand. So since there is no demand, EVs can take advantage of that, and they take advantage of high prices, to discharge into the grid, and take advantage of low prices to charge. So they can increase the profit of the operator, or we can say that they minimizing the charging costs here. Consider in the cases 2A and 2B, as we are considering the power grid constraints here, and they have similar behavior to the case 1A and 1B, but the amplitude here is smaller, and this is because of the power grid constraints limiting my power flow. Following to the analysis of the DLMP, here we have this table which summarizes the average DLMP of the grid, the minimum and the maximum DLMP of the base case, and the cases when we have the power grid. So first we can see that the DLMP remain almost the same average for the both cases. So here we can see that almost the same average. But in the case 2A, which is the one without V2G, we can see that the DLMP would not be reduced, nor maximum or minimum. See, they are the same, the minimum is the same, and the maximum is also the same. But in the case 2B, which is the one with V2G, reduced both minimum and maximum DLMP. So here we can see that reduced the maximum and the minimum. So we can say that a sufficient large EV fleet can affect the energy tariff for all customers, not only for the EV users here. And this could be good. In this case, is good because reduce both maximum and minimum, but it could be bad if the company do not use any kind of optimization. So they could choose to charge the EVs during the high pricing times, and this could increase even more the DLMP, affected not only the EV users, but all the customers, even those ones that do not use the car sharing. So as a partial conclusions, we saw differences with and without V2G, but they are relatively small. And the main reason is because the charging cost is much smaller than the rental profit. There is also other aspects that were not modeled that could lead to the high investment costs, such as the battery degradation and the bidirectional communication costs. And finally, the INESC tariff incentive could not be sufficient for the car sharing operator to use V2G. So we need to investigate other benefits to encourage the car sharing to use V2G. And for this, we create our first sensitivity analysis named load increase. Here, we increased our load in 10%, and problems start to occur at 18 o'clock, sorry, and the power grid needs to be reinforced. And here, the total reinforcement cost was $209,000. And those are the cables that need to be reinforced. So first, considering our case 2A, which is the one without V2G, the optimization without V2G do not reduce the peak demand. Like I said, the optimization without V2G only shifts the peak from the EV charging from peak times to off-peak times. And therefore, the cable reinforcement is the same because the peak is still there. But when I consider the V2G, we can see that most of the cables do not need to be reinforced anymore. But in this case study, 9 electric vehicles were not enough to reduce the cable reinforcement to 0. This branch here still needed to be reinforced. So taking a look here in the decision summary, first, we can see that the total profit in the case 2B is lower than the case 2A. So here is lower than 2A. And this is strange because we saw earlier that case 2B is the one with V2G and 2A is the one without V2G. And we saw that with V2G, we have flexibility, so we can increase the profit. And here, the profit is lower than the case 2A. Moreover, we can also see that the first station decisions change. We need to buy one more electric vehicle. And we can also see that other variables also change. So here, the total profit, the total charging cost is different. The relocation cost is different. And the profit is also different. And more here, we can see that the meeting demand is lower. So which is happening here is that the DSO is affecting the car sharing decisions. And this is happening because the weight of the DSO, the costs of the DSO are much higher compared to the car sharing. So we need to balance the decisions here to get the best trade-off of the agents. So we created a second sensitivity analysis and we named that a multi-objective approach. So we balanced the objectives with weights and we changed those weights. For this, we're still considering the 10% load increase scenario. And since only the case should be changed, we are considering this case for the analysis. So here, taking a look in this table, for alpha equals to 1, here, this first line, we can see that case 2B become case 1B, is the one without power grid constraint. And this is happening because here, for alpha equals to 1, only the car sharing decisions matter in my problem. So the DSO cost doesn't matter at all in alpha equals to 1. And since we do not have any kind of budget limits for the DSO, they expand as maximum as they can in order to maximize the car sharing problem. And the problem becomes the case 1B. For alpha equals to 0, we have here this last line. EVs is just an asset for the DSO because the car sharing profit doesn't matter, only the DSO decisions matter. So the profit is minimum. But the extreme values do not represent a good trade-off in reality. So if both agents are willing to make a fair agreement, the decisions that bring the best trade-off are within 0.9 and 0.5, because between 0.4 and 0.1, the decisions of the DSO start to affect the operation of the car sharing, and they start to reduce the profit. So as the conclusions of this work, we saw that under normal load, planning considering V2G and ignoring the power grid constraints is the most profitable, but only by a small amount, 0.06%. And this planning might be risky for the car sharing operators because the power grid may not be able to cope with this power flow. So this scenario probably will not happen in the reality. But if they opt to coordinate their planning with the DSO, the charging cost increases 0.24% compared to this one. The DLMP peak reduced in 1.5%, and the peak demand reduced in 5.1%. But there we saw that there is low incentive to use V2G given the additional costs. So under the increased load scenario, without V2G, we saw there is no change in the car share profit, and therefore there is no benefit to the DSO. But in the increased load scenario with V2G and in the grid trade-off, the car sharing profit reduced 5%, and the DSO reinforcement cost reduced 66%. So the car share benefits brought to the DSO, such as the reinforcement costs, the DLMP peak reduction, and the peak demand reduction, could be converted into some financial compensation that were not modeled here in this problem, and through public policies or bilateral contract. And both agents would win in this situation because the car share would increase its profit and the DSO would also reduce their costs. I would like to acknowledge those institutions that helped here in my career and in this work. And if you are, I do not have time to present all the work here. So if you are interested to access the full work, here is the link. I would like to thank you for your attention.
Okay, Leonardo, thank you very much for the presentation. So a lot of questions popped in my mind. I'm sure that also from the audience we have perhaps some questions, but as usual, I'll try to break the ice here with some questions. So I saw this part of the vehicle to grid integration, and one of the aspects that we usually need to consider is the degradation of the asset, which is in this case the EV fleet that we may have in terms of car sharing or any other business that uses the electric vehicles have a battery on it. So one of the questions that pops in my mind is how do you dealt with the potential loss in value for an asset that is using a service that has on demand a discharging cycle for a battery? And with that in mind, what would be the best strategies to avoid early degradation of batteries of these assets that you have on the car sharing?
Yeah, it's a good question. The battery degradation was not modeled here, but we have that in mind, that this is one of the major problems that for using V2G. And for future modeling, we are considering using the battery degradation in the objective function. We can equate this within equations, and probably what would happen is that V2G must be really well compensated by the DSO to compensate this degradation. So that are in the planning for the future works.
Okay, another question that I have is in terms of the practicality of this kind of solutions. And perhaps you can talk a bit more on that, because nowadays it's still a very early stage for vehicle-to-G solutions to be a normal or a solution that we see everywhere in car manufacturers. In fact, the manufacturers are at some point restricted in terms of the use of vehicle-to-grid approaches. So with regards to electric mobility, would you see this as something viable in the next years? Because the business model, as you said, needs to be rewarding and has to be a high value for the service being provided to support the grid. But in fact, currently the solutions are not so many for vehicle to grid. So would this make sense for other kinds of electric mobility, because we can differentiate from private and single user mobility from, let's say, large mobility of, for instance, buses and so forth. So in terms of what could be a vehicle to grid approach right now, which seems to be fairly limited, how would you see this in the next years? And how could you validate this participation from the owner side?
Yeah. Yes, vehicle to grid yes, it's difficult to implement, but with this methodology, considering controlled fleets, such as shared vehicles, buses, taxis, it's easier to use the V2G because it's a company, we can say a person that controls all the EVs. For private users, we have to consider aggregators, and the aggregators will group the electric vehicles so they can have some influence, because one EV cannot help the power grid problems, but a fleet of EV can. And it's much easier for the DSOs, for power utilities, to make contracts with one company. And they can rely on contracts, bilateral contracts. For example, they say, you can sell me some X energy during some times. And we cannot rely on private users this, because they can make a contract, but they can easily break this contract, because let's say they say, I will not use my EV, and then he uses his EV, and the DSO loses the power, and who's gonna pay that? And probably they will have a fine, but this fine will not does not bring back the energy. So I do believe that the V2G application is better for controlled fleets, because the operator can ensure that the energy will be injected in the power grid, because they can only stop the EV. Okay, no one will use EV anymore because I'm selling his energy now, and this is more profitable for me. So I believe, and this is better for the DSO, rely on the controlled fleet than private EVs. So for near future, I believe that this would be, for me, is the best option. So we need to sell this for companies that this is the best option.
Regarding that, I have yet another question, since we don't have any more participation on the Q&A. Regarding the part of the cost that you assume for the vehicles, you did assume the whole cost of the purchase of a vehicle, such as a direct purchase of a vehicle as new, if I got it right. Would it be also possible to do in the sort of the depreciation of the vehicle itself, because that's also on the map, because the vehicles do lose value as an asset over time, and that perhaps could also be modeled. So how easy would it be if you didn't do it, or if you did, what was the results?
Yeah, actually, this is a business model for most of rental companies. They use not only DV for conventional vehicles too. They own most of their profit does not come from rental, and is for reselling the vehicles. They buy the EVs, they rent for EVs or conventional vehicles. They rent it for 1 year, 2 years, and then they resell it as used cars. And here in Brazil, that's the most profit of these companies are coming from reselling the cars, not for renting. And at first in this work, I try to put this and to resell the vehicles because they lose value. But as let me show here, here you guys can see I put 1 year as a planning horizon, but this model can consider many years as we want. But the simulation times took too much. And one of the improvements that we are considering here is make a vendor's decomposition to accelerate the optimization, and we can increase the years, and therefore considering another things that cannot be considered in 1 year, for example, selling the cars and buying another ones.
Okay, so we already got a very good glimpse of the work that can be done following up this one that you already did. So thank you very much for your good presentation. Also thank you, Carlos, for his good presentation. Just to remind everyone that participated here that this material will be available online on a video, hopefully with a better quality from the Carlos presentation, but still online. So thank you again, Carlos and Leonardo, for joining us here on this afternoon, and thanking the audience for participating, for attending this this webinar. So a good afternoon to everyone, at least in the Portuguese side, and see you in the next webinar. Bye-bye.
Bye-bye. Thank you all.